Okay, we're going to do one last video about batch reactors and energy balances. And this is the special case where you have no heat input to the reactor at all. And so, you might think, well, this means that I don't have to worry about temperature effects, but actually this is maybe one of the cases where you have to worry about them a lot. You have no mechanism to control the temperature, so there can be quite large changes. Basically, we're going to go back to our batch reactor design equations, and we're going to put in Q equals 0 into those. We had two cases. We had the constant pressure incompressible contents case, or incompressible contents case, and that was this equation, and we're just crossing off this. So you see here that you're going to get a clear relationship between the changes in temperature as the reaction proceeds and the heat of reaction being made by all the reactions happening in the reactor. In the other case, we were thinking about constant volume reactors with compressible ideal gases. Okay, so this gave us a slightly different equation, key difference being right in here, and the difference in the two heat capacities. Okay, again, we cross off the Q term, and you get a relationship that's mostly between the enthalpy of reaction happening and, in this case, a PV correction for each of the new species being formed, and change in temperature incurred by species in the reactor. So there are some particularly interesting cases that come from the interplay between the reaction progress, the heat of reaction, and the temperature of the contents and the kinetics. If you have an exothermic reaction and it's irreversible, then what tends to happen is that because of the Arrhenius law, as the conversion goes up, there's heat generated in the reactor, and that drives the temperature of the contents upward. As the temperature of the contents goes upward, the rate constant increases, and this can be quite dramatic effect. So even though the conversion's going up and at isothermal conditions your rate would tend to go down, this one tends to be very strong and very sensitive to temperature, and it could drive the rate to really high levels for a while. Okay, so you're going to work an example on Wednesday and Friday, looking at an example of a batch reactor explosion. The other interesting case is when you have an exothermic and a reversible reaction. Now the conversion can go up, which again heats the contents of the reactor, but now that drives the equilibrium constant downward, and so you start to, in these cases, run into a limit by how far the reaction can go. It basically limits itself at equilibrium. It's really interesting. So you start with a closed system and you end up with two different equilibrium conversions depending on whether that system is allowed to exchange energy with the surroundings or whether it is confined and operating adiabatically. So usually you're going to get from analysis of these things, you're going to get a direct T versus X relationship by just going through and eliminating T. So remember we before set up these problems where we had a species balance that gave us how X depends on T and an energy balance that gave us how the temperature depends on T. And usually these things are quite tightly coupled to each other. But the way that they are coupled to each other for an adiabatic reactor configuration is that you can usually just eliminate the dependence on T altogether and get a direct relationship between T and X. That's what I mean by that. So let's walk through and see how that happens in practice. So we're going to consider a reaction at constant pressure. It has a non-zero heat of reaction, and we're going to find the temperature as a function of X for an adiabatic batch reactor. So the energy balance, going back above to the constant pressure case, we have a energy balance that says that the total heat capacity of the contents times the derivative of the temperature with respect to time plus the rate of the reaction times the enthalpy of reaction has to be equal to 0. We can go back now and use the stoichiometry. This is a valid stoichiometric result for any reaction that takes a single A molecule and converts it into products, however you've written everything else. So we have R times V must be equal to the total number of initial A molecules present times the derivative of the conversion with respect to time. Okay, so you can always go back and use this to write everything in terms of conversion. It's convenient in this case to go ahead and multiply the whole equation back by V, right? So remember, in these equations we started out with the Q over V to get rid of it on these terms. But in this case, it's actually pretty convenient to go ahead and keep it here because now this object, this heat capacity multiplied by the volume, remember was a volume basis heat capacity. So this is now the total extensive heat capacity of the entire mixture sitting out here. You can write it in terms of the total number of moles. You can write it in terms of a sum over the heat capacities of every individual species multiplied by the number of moles of that species. So you can get this in a lot of different forms, and that makes this way of writing the equation particularly convenient. So here's my temperature derivative. Then I have the number of moles of A, derivative of X with respect to T, and delta H reaction. Now, in many cases, we can basically think of this delta H reaction as an almost temperature-independent quantity. So, when you see delta Cp equals 0, for example, then as I integrate to higher and higher temperatures, the heat of reaction is not really changing. Now, that's not always the case. Sometimes the story I'm going to show you here becomes a little bit more complicated because there can be some hidden temperature dependence inside this term. All right, so what we're going to do now is to go through and eliminate T and solve for the dt dx. Okay, so we eliminated the dt's in this equation, and we just arrange it so that it's dt dx is equal to minus delta H reaction, number of moles of A in the initial charge, divided by the total heat capacity of the entire reactant mixture. Okay, and now we see that we can integrate this directly. If this thing is roughly constant, then we can integrate that directly and get T is approximately equal to the initial temperature minus that constant, which has units of temperature. If you go through and look at this, the units of temperature pop out of the heat capacity in the bottom. So this is basically a temperature here, and then you multiply this temperature by X. What is the physical significance of that temperature? Well, it is the temperature that an adiabatic reactor would reach if it was able to go all the way to 100% completion. So this is the adiabatic reaction temperature, and it's just that coefficient in this formula. So notice that when delta H reaction is negative, we get a cancellation of the two negative signs, and delta T adiabatic is positive, which says that if you have an exothermic reaction, and you operate the reactor adiabatically, it will climb in temperature, sometimes dangerously so. All right, so we eliminated time, but it's still true that this T versus X relationship is going to give us a very simple way of incorporating the coupling between temperature and conversion in equations that describe the dependence of these quantities on time, right? So we'll see some examples of this where you're wanting to predict conversion as a function of time and temperature as a function of time, and this relationship really helps you do that in a simple way. So please see the worksheets and the example problems for lots of analysis using these kinds of things.